Hey, welcome back. In this video, we're going to continue looking at topic 1.7. In the last video, we looked at ways of calculating measures of center, like the mean and the median, as well as positions, like the quartiles or percentiles. And in this video, we're going to look at three different ways to calculate measures of variability or spread. All right, so the most basic way of measuring variability is to look at the range. The range looks first at the minimum and maximum values, and then how far apart they are, right? So we want to measure kind of the overall spread for the whole data set. Okay. So the formula is just max minus min. For this example, it would be 8 minus 1, which is 7. Now, the way you can interpret this is you can say that the values of this distribution are spread across 7 units. So if these were like points that students scored on a quiz, we could say that the quiz scores for this class are spread across 7 points. All right, so the range isn't that great of a measure of spread because of the risk of outliers, meaning that if there was an outlier in the data set, it would artificially inflate the range, right? If that 8 was a 20, right, then the range would grow very fast just by changing one value. So to avoid the issues of outliers, we might think of ignoring the lowest values in the data set, ignoring the highest values of the data set, and just looking to see how much variation there is in the middle. Okay? And so this is the interquartile range. So we're first going to divide the data into quarters. So 4 equal sized groups. Okay, so there's 13 values here. So we have 6 lows, 6 highs, and 2 is the middle value. And then the lows and highs can be split again into making 4 groups. Okay, so we have the first quartile mark is equal to 1. The median is equal to 2. The third quartile is 4.5. Okay. So essentially what we're going to do is we're going to say, okay, this first group we know is the lowest of the lows. We're going to ignore those. And this last group here is the highest of the highs. We'll ignore those. And we're just going to focus on the 2 groups in the middle, right? That's the middle 50% of the data set of the distribution. And let's look at how much spread there is in that middle 50%. So we're going to look at the gap or the distance between the quartile marks. Okay, so from 4.5 to 1. Okay. So Q3 minus Q1 is the formula. In this example, it'd be 4.5 minus 1, so 3.5. Okay, so the range or spread of the middle 50% of the distribution is across 3.5 units. Okay, the values of the middle 50% are spread across 3.5 units. Right, the third and final way that we're going to calculate variability is something called the standard deviation. Now, this is a definition. It's the average distance from the mean. So if we were to make a dot plot and then measure the distances of each dot to their mean, and then average all those distances, in essence, that's what the standard deviation is. So I'm going to work out an example in Excel on how to calculate the standard deviation. Okay, so we have here the formula and then a bunch of values. I think these are the same values that I was using in the example for range and IQR. All right, so let's talk about this formula. There's a lot of mathematical symbols going on, and understanding order of operations is really important to understanding this formula. All right, so this formula is asking us to take each individual x value and subtract the mean. Okay. So that's going to give us a sign distance. Values above the mean will be positive, and values below the mean will produce a negative distance. Okay. And then we're going to go ahead and square those distances, and that's going to make everything positive, which has some beneficial effects. We'll sum all those square distances, and then we're going to divide by n minus 1. So in essence, we're going to average those square distances. But because they were squared, we're going to take a square root, and that's going to return us to the original units of measurement, right? Because squaring is going to make the units squared units. Okay, so let's go through this example. So the first thing I need to do is I need to find what the mean is because I'm going to be subtracting it. Okay. So what we'll do is we'll find the sum of all of our values here. Okay, 39. And then we'll divide by how many values we have. I believe there are 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah. Change that. All right, so I have a mean of 3. So now the formula says, okay, take each individual value and subtract 3. So we'll do 1 minus 3, 1 minus 3, 1 minus 3. Okay, oops. 1 minus, equals first, equals 1 minus 3. Try that again, equals 1 minus 3. Okay, well, let's just do this because I don't want to have to type that for every single value. So what I will do is I will just create a formula. So I want this cell minus 3. And then I will just copy that for the rest of the cells. Okay, so now I've essentially subtracted 3 from every value in the original data set. Now, what if I were to sum these, right? Because the natural thing would be, okay, well, let's just average those. But the issue here is that if we were to try to average these sign distances, we would get an average of 0 every time because the sum is going to be 0 every time because positives and negatives end up canceling each other out. So there's an issue with sign here that we have to correct, and the way we correct it is by squaring. It's going to make everything positive. So I'm going to take -2 and raise it to the second power, and then I will do that for the rest of the values. Okay, so -1 squared is 1, 0 squared is 0, 2 squared is 4, 5 squared is 25. So what parts of the formula have we already done? We've subtracted the mean from each value, we've squared those results, and now we're going to sum that. Okay, so I'll just put it down here on the bottom. We'll sum all these squared deviations. Okay, we get 54. So we're going to take that sum and we're going to divide it by n minus 1. And that is called the variance. So applying this formula with the exception of the square root operation produces the variance. And then taking that square root gives us the standard deviation. Okay. So we're going to take the sum, 54, divide by n minus 1. So there were 13 values. So I'm going to divide by 13 minus 1. Okay. So I get a variance of 4.5. Now the reason why we don't use variance is because it has squared units. Right, because we're working off these numbers here, which were squared. Okay? So to return to the original units of our measurements, we have to take the square root, which is why our formula has that square root symbol around everything. Okay. So finally, we'll take the square root of 4.5, and we get a standard deviation of 2.12. All right, now, obviously, finding the standard deviation by hand is very tedious. So your graphing calculators, computer software, even Excel can do these things very quickly automatically. Right? You just have to know the right command. So in Excel, if I wanted to know the mean, I would use the command average and then highlight my data set. You can see 3 is exactly what we got here. If I wanted the standard deviation, there's a couple different commands. So we want standard deviation.s. Okay. That means that we want the standard deviation of a sample, right? We're assuming that these are values of a sample, not values of a population. So let's highlight the values of our sample, and there it is, 2.12. So on the AP exam, you are not going to have to calculate the standard deviation by hand, but you are going to have to know what that number represents. Okay? And it represents the average distance of the values from their mean. All right, so I want to do one last thing here, which is to talk about what happens when we change units. Or if we transform our data. All right, so let's look at that data set that we had values from 1 through 8, and then let's transform them, right? So let's say these were, scores on a quiz or something, and let's say that, maybe I made a mistake on 2 of the questions, so I'm just going to add 2 to everybody's score. So then the transformed data set would be 2, 2, 2, 2, 4, 4, 4, 5, 6, 6, 7, 7, and 10. All right, so we've got dot plots of the original scores, 1 through 8, and then a dot plot of the transform scores, 2 through 10. Okay. Let's take a look at what's changed. Did I make a mistake? Must have made a mistake. 2, 2, 2, 2. Oh, yeah, it's supposed to be 3. Okay, let's edit that. Okay, I said I was adding 2, so this would be 3, 3, 3, 3. Okay, there we go. All right, so that should be right. So everything, all the scores, just shift 2 units to the right. We're adding 2 to everybody's score. All right. So let's take a look at what's changed here, right? The original mean was 3. The mean of the transformed scores is 5. Okay. The minimum was 1. Now it's 3. First quartile was 1, 3. 2 to 4, 4.5 to 6.5, 8 to 10. So all of our measures of position, right? Means, medians, quartiles, min and max, right? Everything bumps up by 2 because all the scores bumped up by 2, right? But look at that standard deviation, right? It's the exact same, right? Because the points of the transform scores are not more spread out, nor are they less spread out. They have the exact same spread. They've just been moved or shifted over. Okay. So our measures of variability, our measures of spread stay the same, right? The standard deviation is the exact same. The range is the same, right? 8 minus 1 is a range of 7. 10 minus 3 is a range of 7. Okay? The IQR stays the same. 4.5 minus 1 is an IQR of 3.5. 6.5 minus 3 is the same IQR. Okay? So if we add a constant to every value in a data set, our measures of center and measures of position will change by that same value, but measures of spread remain the same. Okay, so let's think of another scenario where maybe I don't add 2 points to everybody's score, but maybe I want to rescale the scores to match something else in my gradebook. So maybe inputting a score of 8 in the gradebook doesn't make a whole lot of sense. So maybe I want to make this out of 100. So I'm just going to times everything by 10. Okay, so then I'd have 10, 10, 10, 10, 20, 20, 20, 30, 40, 40, 50, 50, and 80, right? So maybe those scores make more sense for my gradebook. All right, so now we can see here are the original scores. They all fell between 0 and 10. And here are the transform scores, right? Everything got multiplied by 10. Now let's look at measures of center first, right? The mean was 3, now it's 30. The median was 2, now it's 20. Shouldn't be that surprising that our measures of center increased by a factor of 10, right? They were multiplied by 10 since all the values were multiplied by 10. All right, let's look at measures of position, right? The minimum, 110. First quartile, 110. Third quartile, 4.5, 45. Maximum 8 and 80. So measures of position also multiplied by a factor of 10 as well. Okay. How about measures of variability? Okay. Our standard deviation, 2.121, and now 21.213. All right, so you can see that all that's happened here is the decimal point has moved over. It too has increased by a factor of 10. And we can see that visually, right? The original scores are very tightly grouped together, but the transformed scores are much, much more spread out, and they're spread out by a factor of 10. They're 10 times as spread out. Okay. This is true of the range, right? The original range is 8 minus 1, so 7. The new range is 80 minus 10, so 70, right? 70 is 10 times bigger than 7, right? We can say the same thing for the IQR. 4.5 minus 1 is 3.5, but 45 minus 10 is 35. 35 is 10 times bigger than 3.5. So I guess the moral of the story here is when we transform the data by multiplying, measures of center, measures of position, and measures of spread all change by that same factor. In this case, it was a factor of 10. Okay. If we do something like just add a constant though, adding a constant will change measures of center and position, but has no effect on spread.